now that we have derived expressions relating the strains and the displacement field, let us go back to our earlier example, where we qualitatively demonstrated that if you give me displacement field, we can tell looking at the figure and so on. Now, we can quantitatively evaluate them, because what you all need is displacement field. Okay. So, let us do that. Simple calculus is required to do that. We are given the displacement field. So, once again we will do left hand side and right hand side separately. For the left hand side case, this was the displacement field and we had 2 alpha minus beta x. These were the conclusions which we arrived there. Okay. No normal strain, no shear strain, there was rotation. Just looking at the diagram, okay, figure initial state and final state. Now, let us evaluate that. The normal strain is epsilon x x is equal to dou u x by dou x, and in this particular case the x displacement is not a function of x. You do not have x on the right hand side, which means that if you partially differentiate with respect to x, you get 0. We said no, we are now quantitatively shown that it is indeed 0. Now, what about y direction? Dou u y by dou y. You look at this expression for the y displacement, there is no y there, and then if you differentiate with respect to y, you get 0. Okay. So, same conclusion as we have arrived earlier, but now quantitatively. Now, what about shear strain? Dou u y by dou x, differentiate u y with respect to x, you get minus beta, and then we had dou u x by dou y. So, differentiate this with respect to y, you get plus beta, giving you 0. So, now the shear strain is also 0, that is what we inferred from the figure, initial state and the final state of the figures, but now we have quantitatively shown that it is 0. Okay. In fact, the minus sign here has been chosen so that you do not have any shear strain in this particular case. Now, let us evaluate the rotation. Omega x y is half of the earlier same derivatives with the minus sign. We also discussed how to remember that. So, now it is half minus beta, but now it is minus beta here, earlier it was plus beta, it just got cancelled, but now it is half dou u y by dou x, differentiating this expression with respect to x gives you minus beta, and then differentiating this expression with respect to y gives you beta, but you have additional minus sign. So, if you evaluate, you get minus beta, that is what we said, rotation is yes, but what is the difference now? Quantitatively we evaluated that it is minus beta. For example, beta was 0.05, so omega x y is equal to minus 0.05. Now, what else can we infer? We assigned a positive value for anticlockwise rotation, negative for clockwise rotation. Now, we have got a negative value for rotation, which means that the element should have rotated clockwise, and that is what we see here. Okay. So, qualitatively we can say that there is rotation, element has rotated clockwise, but now we are quantitatively saying it is minus beta. Okay. That is the difference from the earlier discussion and the present discussion. Okay. Now, just let us repeat this for the right hand side case. We said that the displacement field is almost same with a small change, minus beta to plus beta on the for the u y vertical displacement. Let us see what is the effect. We have already seen the effect, no normal strain, there was shear strain and there was no rotation. Okay, that we can infer from the figure itself. Now, let us quantitatively evaluate that. Epsilon x x is dou u x by dou x, same expression for u x, so obviously only sign of beta has changed. Okay. So, differentiate u x with respect to x, it is 0, u y with respect to y, it is 0, no normal strain. What about shear strain now? Dou u y by dou x, so differentiate this expression with respect to x, now you get plus beta. Remember, earlier it was minus beta, now it is plus beta. What about second expression? You differentiate u x with respect to y, of course like earlier beta, now they add up, earlier they cancelled, now they add up giving us 2 beta, which means there is shear strain. That is what we conclude from the figure as well. Now, what about rotation? Omega xy half of the earlier two derivatives with a negative sign. So, half of beta minus beta cancels out, giving us no rotation. Okay. Same conclusions as we have arrived qualitatively, but now quantitatively we are saying yes, that there is shear strain, but no normal strain, no rotation. One more point, we said the shear strain is positive when it becomes acute, okay, it becomes acute angle. That is what we are seeing. Earlier we had at right angles to each other, and it has become an acute angle, and it should result in a positive shear strain, and we have got that as 2 beta. Let us say beta is 0.05, we have got that as positive. So, whatever qualitatively you have seen based on the displacements have now been related to displacement gradients, and we have evaluated them quantitatively. Okay. Another example on relating displacement to strains. Okay. Look at the title of this slide. Title says experimental measurement of strains and rotation. Okay. That has to be kept in mind. We will discuss about the significance of that, but right now what is the significance? You have a plate, and then you mark some points, a force is applied, and then the points get displaced, and we know the coordinates. We have, this example is not new to us, we have already seen when we discussed about 2 dimensional displacement field, displacement gradient. And then of course, initial coordinates are given, the final coordinates are given. Okay. And the difference between the earlier example and this example is that earlier example we are given a displacement field as an expression, look little more mathematical. Now, the salient feature of this example is that we are given the coordinates, which means that they are measurable. You have a plate, and then there are some initial state, let us say you applied some force, something happened, some change in angle or length, etc., and then you can find out the new coordinates. That is why the title says experimental measurement of strains and rotation based on the coordinates. Okay. So, let us quickly read. Figure shows the coordinates of a rectangular plate ABCD, the coordinates are given, okay, before deformation. If after undergoing 2 dimensional strains, okay, the new coordinates are also given, okay. Find the normal strains epsilon xx, epsilon yy, this is new. Okay. Earlier the question was find the displacement gradients, now the question is find the normal strains epsilon xx, epsilon yy, shear strain gamma xy, and rigid body rotation omega xy. Okay. Now, earlier also we in another example we made this assumption. The assumption for this particular case is that if you look at the diagram, the rectangle becomes a parallelogram. Okay. And remember, we discussed earlier that lines parallel to the axis remain parallel. If you draw according to this configuration, they are something like this. Okay. So, they remain parallel, which means that the strains are all uniform throughout. Okay. So, rectangle becomes a parallelogram, strains are same along the entire surface. So, we are going to use one or two of the sides to calculate the strains, and they are applicable throughout the plate, either rotation or strains. Okay, let us do that. These slides are just for recall what I have seen earlier. So, let us go through them. These slides we discussed earlier for calculating the displacement gradients. Now, what did we do? We took 2 particles along x direction. Okay. We took B and C and looked at the difference in x displacement, and then we looked at we took the same 2 particles B and C and looked at the difference in y displacement. Okay. So, that is why our denominator was delta x in both the cases, numerator difference in x displacement difference in y displacement. We calculated that and then found out it was 1 by 150 and then minus 4 by 150. Now, we are going to use this and arrive at physically meaningful values. Earlier they were just gradients. Okay. Now, what did we do next? We took particles along y axis, we took particles C and D and then looked at the difference in x displacement and then difference in y displacement as well. Okay. So, delta y tells you that we considered particles along the y axis, looked at the difference in x displacement, found a value of 2 by 100. Now, next we considered particles along same y direction C and D. Now, looked at difference in y displacement and then found out the displacement gradient as delta u y by delta y and found the value, and that value was 4 by 100. Okay. We also arranged this in the form of a matrix which we later on called as a displacement gradient tensor, and for a particle along one direction indicated by the denominator as delta x, we arranged as one column, and for particles along the y axis we arranged as the second column, and we found out these values. Now, let us see how do we use this to find out the strains and rotation, etc. Now, normal strains epsilon xx is equal to dou ux by dou x in terms of partial derivative. In terms of difference, it is delta ux by delta x, which I have already calculated. We took the line element CB, okay, looked at the x displacement of C minus x displacement of B and the distance between C and B along x axis. How do you find out x displacement of C? Difference in the x coordinate, which is 2, and for B once again difference in the x coordinate, which is 1, giving us 1, the distance between them is 150. Now, what does it tell you? It is a positive value, which means that a line element has undergone elongation. So, if you see compare BC and B dash C dash, you can easily see that there is an increase in length, of course, a small increase in length 1 by 50. Remember, fractional change in length, what you see is difference in length, what we have calculated is this change in length by the original length. So, this what we calculate is a fraction normalized with the original length, what you see here is just change in length, but anyway qualitatively you are seeing a increase in length. Okay. So, let us do that along the y direction considering particles C and D. So, now we have seen the expression for epsilon yy as dou uy by dou y and of course, delta uy by delta y. Now, we are considering particles along y direction looking at their y displacement. So, uy of C minus uy of D and the vertical distance between them. Now, if you consider C, the vertical displacement of C is their difference in the y coordinate. So, 99 minus 100, so minus 1, and for particle D it is minus 5 minus 0 and minus 5. Of course, there is a difference, there is a negative sign because of difference resulting in 4 by 100. So, once again the side the line element CD has undergone elongation of 4 by 100, okay, and that we can see as well if we compare CD and C dash D dash, there is a small increase in length. Okay. So, the normal strains have been calculated. Once again, just to emphasize, earlier we were given a expression for displacement field, we differentiated that and found out the normal strain. Of course, it was 0 in the earlier case, but now we are given measurements, from the measurements we are finding out the normal strain. Okay. So, the strains are measurable, I want to emphasize that particular point. We will take this as a lead somewhere later on. Okay. Shear strain gamma xy dou uy by dou x plus dou ux by dou y, okay, and of course, in terms of write in terms of delta, and let us evaluate them. Remember, for the first term you should take particles along x axis, for example, B and C. For second term particles along y axis C and D, and for the first term look at the difference in y displacement, second term we consider the difference in x displacement. So, let us take the first term, particles along x axis, which is C B, the distance between them is 150, and then in terms of numerator we should now look at the difference in y displacement. For normal strain, if you consider particles along x axis, you look at difference in the x displacement, but now it is the other way. So, consider particles along x axis, look at the difference in y displacement. So, consider C and then B, and the y displacement for the case of C is 99 minus 100 minus 1, and for the case of particle B it is 103 minus 100, which is 3, and so the first term is minus 4 by 150. Coming to the second term, considering particles along y direction, which are C D, the distance between them is 100. Now, consider the difference in x displacement. So, consider C, that x displacement is 2, 150 to minus 150, and of course, D there is no change, it is 150 minus 150, it is 0. So, this gives 2 by 100, when you calculate you get minus 1 by 150. Okay. So, which means that there is a increase in angle. So, if you focus B, C, D and then B dash, C dash, D dash, there is a small increase in angle, of course slightly difficult to visualize, but there is a small increase in angle. Okay. So, we have quantitatively calculated the shear strain based on the measurements of the coordinates using the in terms of the displacement gradients. Okay. Okay. Now, finally, the rigid body rotation, we will calculate now the rigid body rotation. The previous slide we calculated the shear strain in terms of this displacement gradients, and just repeating it so that we can refer for the present calculation, only sign change is required. Okay. So, this is same as what I had done in the previous slide. Now, for the case of rotation, it is half the same two terms here with the negative sign. Okay. So, half into in terms of writing in terms of delta, okay, and now half into minus 4 by 150, earlier it was plus, now it is minus and then 2 by 100, giving us minus 7 by 300. It is a negative sign, which means clockwise rotation, and if you look at compare A, B, C, D and A dash, B dash, C dash, you see a clockwise rotation. Okay. So, that is in line with what we observed. Okay. And so, once again we have quantified rigid body rotation based on measured coordinates. In this example, we had normal strain, shear strain and rotation, all of them were present. Okay. And we also saw how to calculate volumetric strain in terms of displacement gradients. So, let us do that also. So, it was divergence of the displacement field, and of course, 3 terms are there because it is 2 dimensional case, only first 2 terms are there, and so write in terms of difference delta u x by delta x plus delta u y by delta y. We already calculated these values. This is the normal strain along x direction, this is the normal strain along y direction, just sum them up, you get a positive value of 7 by 150, which means that compared to the area of A, B, C, D, the area of A dash, B dash, C dash, D dash is higher. Okay. Maybe little difficult to look at the figure, but slightly we can get a feel, but quantitatively, but remember it is a fractional change in area. Okay. Okay. So, we have seen this and I have specified this as we go along. When we discuss displacement gradient tensor, they were all gradients, they were all derivatives for us in terms of 1D, in terms of 2D, okay, and in terms of 3D as well. Now, when you look at it, we can attach a physical significance to them, either as separate term or combinations. Okay. For example, we have seen what is significance of this term dou u x by dou x, normal strain along x direction. normal strain along y direction, similarly z direction. And then we have seen if you take these two derivatives and then if you add, you get shear strain. If you take difference and divide by 2, you get rotation. So, now it was look like a more mathematical matrix or a tensor with derivatives etc., and then it just told you that how x displacement, that is why remember when we introduced we said how x displacement varies in the x direction, y direction, z direction, how y displacement varied along x direction, y direction, z direction. So, more of a mathematical statement. Now, each term or a combination of term has a very good physical significance, and then if you add all the diagonal elements you get the fractional change in volume. Okay. So, let us write down here. Of course, this was the definition of the displacement gradient, the difference in displacement by distance between the particles. And let us summarize what we have seen so far. First, we qualitatively demonstrated the relationship between strain and displacement field. Okay. We looked at translation, normal strain, shear strain and rigid body rotation. Then we quantitatively related strain and displacement gradients. Okay. Once again for normal strain, shear strain, rigid body rotation, and of course, for volumetric strain as well. In terms of application, we applied it for measurement of strain and rotation. Okay. And we also saw that the physical significance of components either separately or in combination of the displacement gradient tensor. Okay. So, we have seen the physical significance of the components of the displacement gradient tensor, and this last line is the lead for our next lecture. Okay. That the displacement gradient tensor, the components either separately or in combination have physical significance. What is that physical significance? How are we going to use that? That we will see as we go along, and so that is the lead to the next lecture.